data and signals. Part 2 today, part 2. I will share my screen. So, our lesson today is about digital signals. Before we are taking signal can have more than 2 levels. In this case, we can send more than 1 bit for each level. We are going to discuss the following concepts related to digital signals, right? Like bitrate, bit length, digital signals and composite analog signals, and application layer. So for digital signal, most digital signals are non-periodic. And thus, period and frequency are not appropriate characteristics. Another term is bitrate instead of frequency is used to describe digital signals. The bitrate is the number of bits sent in 1 second, expressed by bits per second. B rate expressed by bits per second. For bit length, bit length is equal to, it's an formula, propagation speed multiplied by bit duration. It's like wavelength in analog representation. Instead of wavelength, we here have bit length and can be calculated through a formula. We are not going to take this for this stage. Okay. So we said that the digital signal can be in 2 levels or more. 2 digital signals. This figure shows 2 digital signals. The first one with 2 signal levels, and the second one is with 4 signal levels. The first one, as we see, every cycle can represent only 1 bit, even level 1 represent the 0 bit, and level 2 represent the 1 bit. As we know, digital information is all zeros and ones, right? And each 0 represents 1 bit, 0 or 1. So in 4 levels, 16 bits can send in the 1 second. In the 2 levels, 8 bits sent in 1 level. You can count 1 0 1 1 0 0 0 1. These are 8 bits. in one level represent the zeros, and the second level represent the ones. In the second part of the figure, 16 bits can be sent in 1 second. Each cycle, we can send 2 bits. So, level 4 represent the 1, 1. Level 3 represent 1, 0. You remember, when we represent the data with 2 bits, we can have 0, 0, 1, 0, 0, 1, and 1, 1. So 4 levels. The bit rate here is 16 bits per second. The bit rate in the first part of the figure is 8 bits per second. Okay. Then we can have 2 levels, we can have 4 levels for the digital signal transmission. Now, a digital signal has, we have an example, how to calculate the number of bits for each level. A digital signal has 8 levels. How many bits are needed per level? We calculate the number of bits from the formula. Number of bits per level equal log 2 of 8, which is equal 3. The 3 is the 2 to the power 3, which is equal 8. So, if we have 8 levels, then we can transmit 3 bits per level. Each signal level is represented by 3 bits. A digital signal has 9 levels. Another example, a digital signal has 9 levels. How many bits? How many bits are needed per level? When we calculate by the previous formula, number of bits per level, so log 2 of 9 is equal to 3.17. But this answer is not realistic. Why? Because the number of bits sent per level needs to be an integer. Cannot be like this, fraction. Should be an integer, because the number of bits cannot be 3.17 like this. As well as it should be the power of 2. The power of 2 can be 1, 2, 3, etc. Digital numbers. So for this example, 4 bits can be represent 1 level. 4 bits, not 3.17, okay? Another example, assume we need to download 6 documents at the rate of 10 pages per second. What is the required bit rate of the channel? And here go, this is the solution. The page is an average of 24 lines with 80 characters in each line. If we assume that one character requires 8 bits in ASCII code, the bit rate is, we multiply 100 pages multiplied by 24 lines multiplied by 80 characters and multiply bit 8 bits. Then we got how many bits per second? It's 1 million. So to download 100 pages in 1 second, the bitrate is 1,036,3036 bits per second, or 1.6 megabits per second. Another example, a digitized voice channel. As we will see in chapter 4, is made by digitizing a 4 kilohertz bandwidth analog voice signal. We need to sample the signal at twice the highest frequency. So the highest frequency multiply by 2. We assume that each sample requires 8 bits. So the required bit rate will be multiplied, because we have to double the frequency, multiplied by 4,000, which is the 4 kilohertz, multiplied by 8 bits for each sample. The answer is 64 kilobits per second. Another example. What's the bit rate for high definition TV, which we call HD TV? Uses digital signals to broadcast high quality video signals. The HDD TV screen is normally a ratio of 1920 by 1080 pixels per screen. And the screen is renewed 30 times per second. So the pixels you see at the screen are not stable. They are renewed 3 times per second to stay seeing it. So 24 bits represents 1 color pixel. So we calculate easily by multiplying all these numbers and get 1.5 gigabits per second. And this is a very large number and very expensive. So the TV stations reduce this rate to 20 to 40 megabits per second by a process called compression, through compression process. As we met before with the analog signals, the time domain and the frequency domain. So in the time domain, frequency domain for periodic and non-periodic digital signals. Time and the frequency domain for periodic in the first part of the figure. And actually it's rarely, the digital signals rarely to be periodic. But we can see like this, in the frequency domain, we can represent by the way, the digital signal has infinite frequency. And so it is represented by discrete infinite bars in the frequency domain. The frequency can be, this is the full F, 3F, 5F, many levels of frequency until infinity. For the non-periodic, and most of the digital signals, as I said, is non-periodic. time and frequency domains for non-periodic can be represented in the frequency domain like this shape. Now we are going to learn a new concept, which is baseband. Baseband transmission. The baseband transmission means is to transmit digital signals over the channel without converting the signal into analog. It transmitted as it is. So the first computer sends digital signal and the receiver also receive in digital signal. The digital signal go through the channel media as it is without any conversion. So the baseband channel is a communication channel that is able to transfer or transmit frequencies that are near to zero also. We will see in the next. A digital signal is a composite. A digital signal is a composite analog signal with an infinite bandwidth. The bandwidth can be wide. This is the first one, the first part of the figure shows the bandwidth of two low-pass channels. This is another concept, low-pass channels. Low-pass channel is a communication channel that can transfer frequencies that are very near to zero. The low-pass channel can transmit or transfer frequencies that are near to zero. This is a wide bandwidth, low pass, and this is a low pass channel with narrow. Narrow bandwidth means low frequency. Wide bandwidth with high frequency. The baseband transmission using a dedicated medium. We said the baseband that we can send the signal as it is without any conversion, without conversion to analog signals. During what? During the wide bandwidth channel. It should be wide bandwidth channel. Because the digital signal has very high frequency. It's like unlimited. So this channel is a wide bandwidth channel that can transmit the digital signals without conversion. And using this medium or channel, we can have the output signal mostly like the input signal, but not converted to analog. It's still digital, like we have seen here, sending digital and receiving digital signals. So baseband transmission of a digital signal that preserves the shape, almost preserves the shape of the digital signal is possible only if we have low pass channel. As we said, the low pass channel, which can transfer very low frequencies like to zero frequency. And when we know when the frequency is near to zero, then we have like an infinite or very wide bandwidth. As an example of a dedicated channel where the entire bandwidth of the medium is used as one single channel is a LAN. Where we can use this, as an example is the LAN, local area network, almost very wired LAN today uses a dedicated channel for two stations communications, like two computers with a wire represent like this dedicated channel, which can transmit the digital signal without any conversion. In a bus topology, LAN with multi-point connections, only two stations can communicate with each other at each moment in time, what we call time sharing. The other stations need to refrain or wait from sending or prevented from sending data. In a star topology LAN, the entire channel between each station and the hub is used for communication between these two entities. Rough approximation of digital signal using the first harmonic for worst case. We will skip this because you didn't take the Fourier representation. We will skip until here. If the available channel is bandpass channel, now what is the difference between low pass and band pass? The low pass can transfer frequencies that very near to zero, but the band pass, no. We have two frequencies and not zero. We cannot send, if the available channel is a band pass channel, we cannot send the digital signal directly to the channel. We need to convert the digital signal to analog signal. We said, if you want to send the digital signal as it is, we should use a low pass channel, right? But if we want to use a band pass channel, then we cannot send the digital signal directly to the channel. We need to convert the digital signal to an analog signal before transmission. Here, this figure shows how the conversion or the modulation of a digital signal for transmission on a band pass. So to transmit the digital signal on a band pass channel, we have to do the modulation process. This figure illustrates how the modulation process. At the beginning, input digital signal goes through the digital analog signal converter. Then, as we see, this is the input analog signal bandwidth starting from F1 to F2, not from 0. So this is the input analog signal after conversion, goes through the available bandwidth, which is band pass channel. Then this is the output analog signal. The analog signal goes through band pass channel without any problem and received by the receiver. The analog signal is received. This is the output analog signal, goes through another analog to digital converter to retrieve the original digital signal. This is the output digital signal as we see the same one from the sender to the receiver. An example of broadband transmission using modulation, the modulation process which we just show, is the sending of computer data through a telephone subscriber line. At the beginning of the internet, we were using the telephone subscriber line, the line connecting a resident to the central telephone office. Before the cellulars and before now the wireless communication, we was using the telephone subscriber line to connect to the internet or to connect to devices through the internet through the central telephone office. These lines are designed to carry voice with a limited bandwidth. The channel is considered a band pass channel. That channel was considered as a band pass channel. So the digital signal of the computer go to a converter from digital to analog, go through the line as analog, then at the receiver station is converted again from analog to digital, and the receiver can receive it, the receiver computer. So we convert the digital signal from the computer to an analog signal and send the analog signal. We can install 2 converters to change the digital signal, one at the receiver and one at the sender. And this was called the modem. This converter, in this case, is called the modem. So at the beginning of the internet, we were using modem, which we discussed in detail in chapter 5. A second example is the digital cellular telephone. For better reception, digital cellular phones convert the analog voice signal to a digital signal. Although the bandwidth allocated to a company providing digital cellular phone service is very wide, we still cannot send the digital signal without conversion. We cannot send the digital signal without conversion. The reason is that we only have a band pass channel available between caller and callee. We need to convert the digitized voice to a composite analog signal before sending. We will stop here in chapter 3. So maybe next week we will take the part 3 of chapter 3. Any question? Any question? Are you with me?
Yeah, the voice good.
Okay, alhamdulillah.
Yes.
Alhamdulillah. Okay, thank you all. We stop here.
Thank you, Doctor.
Assalamu alaikum. You are welcome. Assalamu alaikum.
Thank you, Doctor.
Assalam. Thank you, Doctor.
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 Thank you.